This tutorial is about operator scope. So as you recall from our introduction to propositional logic, we represent propositions with a variety of symbols. Lowercase letters are used to represent propositional variables. Uppercase letters represent propositional constants. And then we have 5 operators that we will be using in this deductive system. When we write a proposition using one of the symbols, for instance, conjunction, we use this upside down V looking thing to indicate conjunction. And as you remember, this is a binary operator, and so on one side it has a slot that has to be filled by a proposition, and on the other side it has a slot. Both of these two slots have to be filled with a proposition that is a well-formed formula in order for this whole expression to be a well-formed formula. The easiest instantiation of this overall form would be to use propositional variables that are atomic. So for instance, we might write P and Q. So this is a good example of this form, because on this side of the and, you have the square filled in with the propositional variable P, and on this side, you have, in the triangular side, you have Q. Sorry, I changed types of triangles there. So if we look at the overall form, though, the form doesn't really tell us anything about what degree of complexity needs to go in the square on one side or the triangle on the other side, right? In other words, we filled in both of these two slots with an atomic propositional variable, but we could just as easily have filled it in with a molecular proposition constructed out of variables, as long as it's a well-formed formula. So for instance, suppose we had in the square R and S, and suppose in the triangle we just had T. This is perfectly acceptable. Why is that? Because the expression R and S is itself a well-formed formula. In fact, it instantiates exactly the form that we're talking about up here. On one side we have a square filled with a proposition. On the other side we have a triangle filled in with a proposition. So to put it a little bit more technically, the and here, this conjunction, has 2 slots, and each of them are filled with a well-formed formula, in this case an atomic propositional variable. But we can, as this illustrates, this expression, we can fill in any of those slots with propositions of any degree of complexity, as long as we make it clear what is in the slot. And how do we do that? Well, now we need to add a third type of symbol to our other two. So for instance, we have propositions represented by either a lowercase letter, which is a variable, or an uppercase letter, which is a constant. We have our operators, and now we also need to have groupers. Groupers are basically parentheses of various types that show us what propositions need to be grouped together in order to be a well-formed formula. So let's have a look at how we would write this expression using groupers. Well, first of all, we have R and S, and we need to do something with that to indicate that it's a single unit, or it's functioning as a single unit. What do I mean? I mean, it is functioning as a single unit with respect to this conjunction operator, because this whole expression is what goes in the slot indicated here by the square. So the parentheses indicate that this should be taken as filling up that whole square, and then we have our and operator, and then we have the expression T, which is atomic, so it doesn't need groups to indicate that it is contained within the triangular slot. All right, so what this means is that the expression, parentheses open, R and S, parentheses closed, and T is a well-formed formula. How do we know it's a well-formed formula? Because a formula that is constructed of well-formed formulas is a well-formed formula. This is a well-formed formula because it follows, as I show here, it follows the pattern of conjunction with an atomic variable on one side and an atomic variable on the other side. So it's a well-formed formula, and because it's a well-formed formula, then it can fill the slot, as it were, for the conjunction operator to create an even more complex well-formed formula.